Kalka, who's one of the project scientists. So today we'll work through, I want to give overview of what the system is, some of our terminology, what's in the water, a few examples, the kind of site information that we have, and then a little bit about the proposal process that we have in place currently. And then I'll hand it over to Mike Harrington, and he'll go into a lot more of the technical details and the kind of information that we need to help you with your proposals. So the cabled array, and this information is all on the oceanobservatories.org page, but I'll go over it. So in our world, the primary infrastructure is 900 kilometers of high bandwidth, high power cable that runs from a shore station in Pacific City, that little green triangle there, or whatever that shape is, over 300 kilometers offshore to axial seamount, and then there's a southern line that runs from along the base of the subduction zone and inshore to a water depth of 80 meters. Currently we have 18 junction, so that's the primary infrastructure. I'll show you some examples of that. The secondary infrastructure was all built and installed by the UW, specifically was built by the Applied Physics Lab. We have 18 junction boxes, and I'll show you that in more detail. So the primary infrastructure, the primary nodes are those red, orange boxes, and then to get to the main key sites, we have a series of smaller, you can think of them as kind of substations on the seafloor. So we have smaller junction boxes, 18 of those. We have 6 moorings, 2 different kinds. I'll describe those that rise up to 2,700 meters above the seafloor with instrumented wire crawlers. We currently have a little over 140 instruments. And the key thing is, you probably all know, is because of the internet connection, we have two-way communication, so we can change command and control parameters, sampling rates, look angles, things like that. And from day one, the system was always built to be highly expandable. So we aren't using, in most sites, we aren't using anywhere near the power or the bandwidth yet. It was built on time and under budget. John Delaney was the lead during that part of the program until 2014, and we've had 2 successful operations and maintenance cruises. And another one, about 35-day cruise, will be take place this coming summer. I'll just go through. So this is just the agenda. I mentioned that, so I'll skip that. Right now, so we report on all the instruments and infrastructure every couple of weeks or so. 95% of the infrastructure was installed and is installed on the seafloor. The one piece that we've had some issues with are 3D profilers. Those will be, 2 of those moorings will be recovered, and all 3 will be installed this coming summer. So we have a pretty good operational rate right now. About 83% of the instruments are operational. There's 135 installed in about 33 different types of instruments, and you can find out more information about the instruments on the Ocean Observatories page. So this is just a little bit about the primary infrastructure. It was a very successful partnership with L3 Maripro, who designed and installed it. Okay, we're going to catch up here on the video in a second. So hopefully, there it goes. So this shows one of the primary nodes. They're a very large piece of equipment on the sea floor. The cable is buried up to 1,500 meters water depth. Part of the design was to think about operations and maintenance, and so almost all the cables, the primary cables and the secondary cables, we use wet make connectors. They come out of the oil patch, and it means that we can plug and unplug infrastructure on the seafloor without having to recover the primary nodes or the secondary junction boxes or instruments. Each of the primary nodes has 5 science ports. There's expansion ports, pulse per second timing, and we can provide more information. But this just shows you one of the shallow water nodes. It has a trawl-resistant frame on it to prevent fishing issues. So during the installation planning process, we had a lot of interaction with the fishermen in Oregon, and actually they okayed the cable routes, so we tried to keep away from areas of fishing, and there's some no-fly zones on the charts now to let interested parties know where our infrastructure is on the seafloor. The installation of the second infrastructure was done by the Canadian vehicle called Ropos, and there was 85 days in 2014. We had a 55 days in 2015, and then this summer we transferred the operations of maintenance capabilities to the ROV Jason, and that's shown here. So we had, you can see that we have it's a very intense cruises, and one of the things that we emphasize when we talk to PIs is we really work with them to help them with the installation and recovery process so that they understand basically the requirements of the ROV, how long it takes to get infrastructure to the seafloor, weight limits, and things like that. So we have a fair amount of equipment to recover and install every single year, and we're in the process right now. As soon as we come back from cruises, we start in the refurbishment process. So we're undergoing that for next year. Some key things to note is both Ropos and Jason, when Jason was converted, they're designed specifically for cabled work right now. Jason can flip over from science operations to more heavy industry type work, and they can lift up to 4,000 pounds now. And one of the things that is really nice about these systems is they have, if you look on the underbelly there, you can see it on Ropos, there's a latching mechanism under the belly of the ROV, and it latches into, in one case, the cable laying equipment, or on the slide to the right, a shallow profiler piece of gear. I'll show you that in a second. And what that allows us to do is get it through the air sea. It's a very quick transfer of gear, both on and off the deck, but it lets us get equipment, heavy equipment, through the air sea interface very quickly, and also it allows for very precise, accurate placement of equipment onto the sea floor. So it's a great great addition to how we do the operations. This just shows you this is a little bit of the secondary infrastructure. So this is a classic secondary junction box, again built by the Applied Physics Lab, and it shows you that latching mechanism on the top of the secondary node there. These things are about 8 feet long. This one's at the summit of axial seamount. It shows a 3D thermistor array getting ready to be deployed. And then the orange cables are extension cables. We have about 33,000 meters of extension cables on the seafloor right now. They were completely installed in 2014, and all have been operational. We haven't had any issues with any of the junction boxes or any of the cables since they were installed. Each of the secondary junction boxes is modified or set up by the Applied Physics Lab to meet the requirements of the core instrumentation that is supported by NSF for operations and maintenance for the next 25 years, and then also for PIs. So one of the key discussions that takes place is the requirements necessary for your guys' instrumentation in terms of communication and power requirements. And again, these you'll see on the picture there on the bottom, these all have wet mate connectors. In some cases we do dry mates, but most of the instruments are now wet mated connectors to allow the flexibility to recover and replace these without having to pull up the junction box. The other thing that's nice about this is, again, with expansion capabilities in mind, each junction box has a separate port that allows the junction boxes to be daisy chained, so we can set up multiple junction boxes in a given area. We have, I'll show you a picture of the fantail of the Sekuliak that we used last summer. We have very intense planning discussions with the ROV operators. This just shows you one for Ropos, but the same thing happens for Jason. And because of operations and efficiency considerations, we really load up the ship. There's barely any walking space, and so this just shows one of the deck layouts for one of the cruises that we had. And this slide here shows, this is on the Sekuliak, but it shows the first leg of last summer's crews, which are typically dominated by shallow profiler work and a few junction boxes, but we really stack the decks as close as possible with gear so that we can get as much done on a single leg. Typically we have 3 legs each summer now, leaving from the UW or Newport and coming in and out of Newport, Oregon. So So I'll show you a little bit of some of the infrastructure and some of the kind of site characterization that we have. The way that this design was set up, you might wonder, for those of you newcomers, how we chose the sites that we did. There was a request for assistance from NSF several years ago. It was an open call without any bounds on costs or infrastructure. There was about 16 proposals and almost 300 people that responded to the proposal request. And then out of that, we worked very hard as part of a science technical advisory committee to pick key sites where we could get the biggest bang for the buck and please as many scientists as possible. And so this highlights the endurance array, cabled array and endurance array, which goes from the slope-based site, which is 2,900 meters water depth, and then up to 80 meters water depth off of Newport, Oregon. And you can see the kinds of science questions that were based, the way that we set up the infrastructure and shows the, both the infrastructure as well as the instrumentation at the site. It's I think a really impressive array out there right now. It's in collaboration with Oregon State University, so we have both uncabled moorings as well as cabled moorings and a series of junction boxes at specific sites, as well as a series of gliders that go from offshore Newport out off to the margin there. There is really no other cabled observatory or density of infrastructure along any margin right now, and so it's a really great opportunity for scientists to do some interesting work, multidisciplinary work on these an area where it's a highly productive margin. We have 2 different kinds of moorings right now. Again, these are all cabled. We have a shallow profiling mooring, which is the one shown to the left there. It's a 2-legged mooring. I'll show you some more examples of that in a second, with a very large platform at 200 meters water depth. And then there's an underwater winch profiler that goes up and down through the water column and has instruments attached to that, as well as on the platform. The second kind is a deep profiler mooring, and it has a McLean profiler that goes up and down through the water column to about 150 meters beneath the surface. And again, these are able to be commanded and controlled from shore. For just a little bit of information about the kinds of information we can provide for you for site planning, as part of the site survey work, we have 5-meter or better resolution bathymetry maps of most of the key areas. And then we have, every summer we go out, and whenever we change a piece of gear, we relocate where that instrumentation or, say, a mooring leg is, and all those maps are provided for you. So if you need help in planning, we can walk you through some of that and some of the considerations. We also have some 3D maps like this, just some cartoon views to give you kind of a sense of where things are. And this just shows this slope-based site that has both a 200-meter platform as well as a deep profiler, and then a series of seafloor instrumentation. Some things that are very helpful, I realize you probably can't see this very well, but we have functional block diagrams that are updated yearly. And these are, I think they're very beneficial. They show every single piece of gear that we have on the seafloor and through the water column, all the different kinds of cables, the connectors, and then all the instruments. And so if people are interested in seeing what's at a given site or what kind of connectors you might consider using, this is a good place to find that information all in one area. If we zoom in on the slope-based site, I'll just show you that in detail. So these are the instruments that we have right there, and then the different kinds of connectors, whether they're dry-mated, electrical, or hybrid. And again, some of that depends on the power requirements that we have for each of the instruments. Worked very hard to walk through the the cycles of when things would be recovered and reinstalled from the seafloor. A lot of the seismic instruments, they can stay out for many, many years. They don't really have any moving parts. Other instruments that get biofouled or have pumps or reagents, we recover every year, and that drives and reinstall, and that drives our O&M crews for the summer. I'll show you a little bit about the moorings. They're a pretty amazing engineering feat, especially the shallow profiler with the optical underwater winch. That's shown on the left there with a winch profiling science pod. And then on the right of that big platform is a stationary platform that has a lot of instrumentation on it also, and I'll show you some video of that. So this thing, it's 12 feet across, about 7 tons. And again, this was built with operations and maintenance efficiency in mind. So both the shallow profiling pod as well as the stationary platform interface there on the right, those are recovered and reinstalled every summer with an ROV using the latching mechanism. And within less than a day, we recover and reinstall both of those pieces of infrastructure. So they are a phenomenal piece of gear. They're working extremely well. They have a variety of sensors on them. This just shows you one of the pieces of gear on the platform interface assembly. So this is the stationary piece of gear. And again, we designed this, APL designed this, so there is about 30% expansion or more depending on what kind of instrumentation you want to put out there. This video will take a minute to, okay, here it goes. So this is how we install these. We latch them beneath the vehicle. We'll recover the shallow profiler, then take the next one down, reinstall it, recover the platform interface assembly, and then reinstall the next one. These have made over 8,000 profiles since 2015. All of them are operational, and this just shows you the winch profiler, optical winch, they're coming in and out of the platform. They're very smart profilers, so if the weather is too nasty, if the waves are too big, there's a lot of engineering sensors on these pieces of gear, so they'll hide their heads beneath the nasty zone and keep profiling. We make currently 9 profiles a day. On a downward cycle, we do step functions because some of the instruments, things like for measuring CO2, you have to stop the platform, hold position for a while, make the measurements, and then start the transect again. But these are pretty amazing pieces of infrastructure, and again, they've since the installation, they've all been operational. So these are the instruments that we have on that. You can see there's a variety of gear. Things that people have considered adding on are things like in-situ flow cytometers or 3D imagers. All these data are, since being installed, have been fed into the cyber infrastructure operated by Rutgers and are available both as raw data right now and many of them through data products, through the cyber infrastructure. And that information is online through the data portal. So I'll jump for a few minutes to Axial Volcano. It's the largest volcano off the coast of Washington, which is why it was chosen. It's erupted in 1998, 2011, and then 2015 it erupted again, both in the caldera as well as to the north. This shows the upper left diagram shows the primary cable. Down at the base there's seafloor infrastructure as well as 2 of the moorings. And then the cable runs the base of the volcano is about 2,700 meters water depth, and the top of the volcano is about 1,500 meters, and it shows the primary node there. And I'll zoom in on that caldera, that down dip depression there, right at the middle of the volcano where the spreading center runs through the top of axial seamount. So we'll zoom into that there. So this is the infrastructure that is now on the seafloor and operational. We have a variety of, it was always designed as an interdisciplinary study site, so we have geophysical instruments to look at how melt is transferred around in the volcano, what happens during there's an eruption, seismic events, whether the volcano is inflating or deflating. We have chemical sensors in the hydrothermal field, so International District and the ASHES hydrothermal fields are instrumented. For scale, those white lines are all the secondary extension cables that run across the caldera. It's about 3 kilometers across, but you can see there's a nice array of different kinds of instruments out there, as well as the HD camera that feeds live video back. Highlighted in yellow, people might be interested in what's been funded right now. NSF has funded 2 proposals, one to add a bottom pressure tilt and current meter, and then another proposal to add on a self-calibrating pressure sensor. So these are PI-driven proposals. In addition to the 2 NSF awards, there's now an industry award and also an international award on the cabled array. So there is definitely opportunities now for adding more infrastructure. This just shows you most of the data are fed into the cyber infrastructure, but the seismic data is also fed into IRIS, which is a national NSF-funded repository site, both nationally as internationally. There's over 200 repeat users right now that download the seismic data, and this just shows you the histogram of the seismic events in April 24th, where there were over 8,000 earthquakes in a 24-hour period. And the seismic gear is sort of interesting because they have to be, this is a short period seismometer shown in the slide there to the left, and they have to be very level. So if you remember those games you used to play as kids where you put the little ball in the holes, that yellow platform there on the triangular shaped platform is there's a little ball in there that when they're totally flat, it's in the center of the leveling field there. So I'll zoom into the ASHES hydrothermal field to show you some of the site characterization data that we have there. It's a relatively small field. So we have mapped all the hydrothermal sites there. Those little red bumps are mostly the hydrothermal mounds. They're small, which make them easily accessible, about 4 meters high or so. And we have a variety of infrastructure there. 2 short period seismometers to look at micro-earthquakes, diking, and eruptive events, 3D thermistor array, HD camera. We also have a couple uncabled fluid samplers there, and then the new ones that will be added on as a pressure tilt instrument and possibly a CTD. We may move it to international. So these data, again, these high-resolution maps are available to you. We also have, for both axial as well as the southern hydrate methane seep site, we photomosaic the entire hydrothermal and seep sites. So we have photomosaics that show you where all the sites of venting are. In this case, all that white area on the basalt is where there's fluid exiting the seafloor. For ASHES, we also have photomosaics of every single chimney. So again, those data are available for folks. During installation, prior to installation, we do detailed imaging, both still and video, of all the installation, all the pieces of gear that are in place. That provides context for interested users, as well as once they're in place, we re-photograph them and again adjust the mapping position every year so that people will know where the instruments are. For proposals for the core instrumentation, we also take verification and calibration samples pre and post installation. Those include CTD samples. We do CTDs. We also have a CTD on the ROV. We have Niskin samplers both on the ship CTD as well as on the vehicle. And then we also can take integrated gas tight samples. Again, depending on what the user community needs, we can help out with those kinds of requirements also. Every year we produce a cruise report that has in the back has a detailed listing of all the instrumentation and infrastructure that we've recovered, and these are available on through the data portal. So for people that are interested in adding on to the facility, our job as the cable array team is to help you do that, make it as painless as possible, and ensure that you have all the information that you need for your proposal. After the webinar, we have one-on-one technical consultations. All these are proprietary, so we make sure and keep it to ourselves. prior to the one-on-one technical consultation, we request that you fill out a technical interface planning form as much as you can. A lot of times people don't know the answers to all the information that we ask for. This includes testing, integration, cables, what kind of cables, help with siting information, what kind of connectors you might, whether you need some help in fabrication, installation, data, all the things that you need to know to get something on and off the seafloor successfully. And we work through that with you. The process right now is that proposers for NSF will go through a subcontract with us that includes costs for testing and integration, any fabrication, installation, things like that, and we work through you with that. We request that all that information is at least 18 days prior to the NSF, working days prior to the NSF deadline, because we have to submit the subcontracts through the UW here, and that allows us time to make sure that all the information is in place so that we don't, we can get it in on your guys' deadline as well as ours. We provide a technical feasibility cost letter. We never evaluate anybody's science or anything. The technical feasibility is just to say, yeah, everything's in place, the right kind of connectors, the cables are there, and then the costs that we have to deal with on our end are also in place. The PIs for the proposers say they want to add 1 or 2 days for installation and recovery. The proposers are in charge of, in most cases, are in charge of putting in a shipboard time request to UNILS, as well as the time for the ROV adjacent. And again, if you need more information, cruise instrument data, site data is all available at the Ocean Observatory's org page, as well as through the OOI data portal. And then every year, as part of our education program at the UW, we run a, we call them Visions cruises. They're the cabled array cruises where we have students on board, but we also have a lot of video of all the sites, as well as digital still imagery and site information on there too. So I think I'll stop there and turn it over to Mike. We can either ask questions now or hold it until Mike. Some questions may be answered by Mike when he goes through the technical program. So, Brian, have you seen what? Okay, great. All right, so excuse me, and we'll transfer over to Mike's presentation here.
Great. All right, thanks, Deb. Yeah, I'm Mike Harrington. I'm engineer at the Applied Physics Lab here at the University of Washington. I've been involved in program for probably the last 10 years or so in all aspects of it, from the initial design through the build, test, and now the operations and maintenance. So this presentation was put together with Dana Manilang, who is the main instrument interface. So most of you, when you will be going through the process of figuring out how to fit your instruments onto the system, she'll be your main point of contact and is really good. She was the one that worked on integrating in all the instruments, all the core instruments into the system, and is very experienced at getting the new stuff onto the system. Also, James Tilley was a source for a lot of the information. He is another electrical engineer. He was the main engineer for all the electronics in the secondary node. He's heavily involved in all the interface into the instruments and knows a lot of the connectors, communication issues. So that's sort of the team at APL that you'll mainly be dealing with bringing instruments on. This is the first time I'm doing the presentation. Dana usually does it, but it should go pretty smooth here. I'll be going through mainly a lot of the engineering details. That Deb did a good job of putting context together for where everything is and how the system works, and I'll be going through some more nitty-gritty details. And then when we have a follow-up consultation later, we'll get into even more details about specifics of the best way to integrate your instrument onto the system. So I'll be going through the quick overview of the engineering architecture. I'll go into a little more detail about the secondary nodes, more details about the different instruments, interfaces, and then the process of how it'll go through and make it ready to make sure that it'll be a success when you put it onto the system. We'll also talk a little bit about what we've learned over the last couple of years for how to bring these instruments and successfully integrate them into the cabled observatory.
We're escaping for just a sec to get it in so it only shows one slide. Okay, maybe this will...
Sorry about this.
Sorry, guys. Okay, great.
All right. Okay. So it's just some high-level details of the system. Each instrument port has a unique IP address, and so whether the instrument is natively an Ethernet instrument or if it's a serial instrument, it'll end up with the unique IP address. We'll convert all the serial data to IP right at that instrument port, and then it comes back over the network all the way to shore. So, essentially the vision is that every instrument out there has an IP address, and it's, no different connecting it to your PC onshore as if it's out a couple hundred kilometers and 3,000 meters deep. And then also we can for power control, each instrument's port, back from shore, we have systems that we can turn power on and off for each port individually, so we don't really bust the power to multiple instruments. So each one we can control and monitor, look for how much current's being used, any ground faults, and completely isolate it if there is an issue with an instrument, so it doesn't affect the other instruments that are on that same node. We do, besides network and power, timing was a big requirement for the system. So we have very accurate timing available to all science ports, 10 microsecond accuracy across the whole system. That was a key requirement for the primary infrastructure, and L3 was able to deliver that accuracy. And then we, provide that in a couple different ways that we'll get to later. And then finally, as Deb talked about, ROV wet mate connectors were an enabling technology for an ocean observatory. There's just no way you could build a system like this without those. And we've had really good success. We use ODI wet mate connectors, and I don't think we've had any failures after they've been installed and working. So it's been a good technology for us. So the next slide is this is a nice graphic that shows all the different types of interfaces in the system and how they connect together. And so from the shore station, there is a connection out to the primary node. Those are the long distance connections, hundreds of kilometers, and those run at 10 kV. And that enables us with the standard telecom cable to provide 10 kilowatts of power to each of the primary nodes in the system. So a huge amount of power. 8 kilowatts is available to be shared amongst all the science ports that are on each primary node. So each primary node can be connected to can pass the 10 kV along to 2 different primary nodes, and then at that primary node it has up to 7 science ports, 5 of which are they're available at 1 gigabit Ethernet fiber, and then 2 of them are at 10 gigabit Ethernet fiber. So it's possible to connect instruments directly into the primary node, but actually right now there's only one instrument that's connected directly to the primary node, and that's the high-definition camera at the ASH's site, and that allows us to bring uncompressed HD video all the way back to shore in real time. All the other instruments go through secondary nodes, and so the MPJ box there is a typical secondary node. It plugs into a primary node using plus minus 187 volts, so 375 volts. You could bring again, 8 kilowatts directly to an MPJ box, but that's how much shared between all the ports on the project. And then the MPJ box is what typically all the instruments will connect to. And there we'll go through the different types of interfaces that you can connect to. But basically, we configure the junction box for the particular instrument, and we'll get into those when we go through it here. So again, these are what the final interface to the instruments are typically. The secondary nodes were designed, built, and maintained here at APL. So it's pretty easy for us every year to adjust them as needed. For if there's new instruments coming on, we can configure them as needed for those. We typically, I guess over the last 2 years, we typically bring back about 5 or 6 MPJ boxes a year. So there's 18 that are out there on the seafloor, and we'll, as part of our normal maintenance, planned maintenance cycle, we'll be swapping out 4 or 5 of those. And then if we have new instrumentation that we know that's coming, we can plan their maintenance around and configure them as needed to support any new instrumentation or configurations that are out there. Each secondary node is pre-configured, so the voltage, the type of voltage, power, and communication that goes out each port, and the connector type is all planned out ahead of time, configured, so you can't go in and swap it in real time out there. And that was a design choice we made 7 years ago. I think it's worked out pretty well for us going forward, but that's how we go through and do that. Let's see, the connections to the instruments can be wet mates or dry mates, and again, we'll go through that a little bit more detail. And one last point is that basically instrumentation that's close to primary nodes, that 8 kilowatts is available, and in most places, you basically have unlimited power and bandwidth. 10 gigabits and 8 kilowatts of power available. As you get further and further away from a primary node, because of losses in the cable and the amount of copper we can get in the cables, you have to be a little bit more careful of how much power the instruments use, and we have to allocate it and do a little bit more planning. But so far, we've been able to accommodate everything at the places that we've gone. So this is me. Actually, we don't have virtual camera image, but that's me looking at the guts of this is an MPJ box that's on the bench here at APL, and you can see sort of the connector panel in front. You've got in the bottom 2 large connectors. Those are fiber optics going in and out of a MPJ box, and then all the other cables are going off to instruments. And we've got quite a bit of custom electronics, as well as some COTS. There's a network switch and CPU in there, and then quite a bit of custom electronics for power conditioning, monitoring the powers, being able to control power going on in there. Deb showed a picture of this, but this is one of the secondary nodes getting installed underneath row posts going into the water, and one on the seafloor going on. You can see the cables going out. So here are the common interface communication options that we support all the installed instruments right now. So either standard Ethernet at 10/100, so it's just a 4-wire interface, so not 1 gig-E, but 10/100. RS-232, majority of the instruments out there just use standard 232 interfaces. We can support RTS and CTS if needed. 485 and 422 are options if you have to go further away from the instrumentation, and we use those as well pretty successfully. Power options. So again, each instrument port gets its own DC to DC converter. So internally to the node, it'll have 375 in the MPJ box, and then it'll get converted down to either 48, 24, or 12 volts. And we can either have a 50 or 200-watt converter depending upon what the instrument's needs are. So those are the common options for all the instrumentation that's out there. Let's see, I think there one. Go back one. So timing options. Again, we have very accurate timing available to the instrumentation. Some instruments that's critical, for the seismometers, they definitely bring out and need as high as accuracy as possible. Some instruments, CTDs, it's not as critical to get that super accuracy timing. And so we can tailor the solution for whatever the needs are of the system. So if it's an Ethernet-based instrument, it can use NTP, so we have an NTP server back in the shore station, and they can just turn on and connect to that and get approximately 10 milliseconds of accuracy. We have PTP enabled in the system, so we have in each of the MPJ boxes, we basically have a PTP master that's slaved back to the shore station, and then all of our Ethernet switches downstream from that are PTP enabled. So if someone does need very high accuracy timing for an Ethernet instrument, that is available. Right now, I don't think any instruments are using that. We have hydrophones that potentially could use it, but I don't think that any of them have actually used it. Most of the instrumentation so far has fallen back and uses pulse per second and time of day serial strings directly to the instrument, and that's been a successful model, just because they're used to dealing with, having, a lot of them are used to having a GPS system to hook up to. And then also for instrumentation that is just a normal serial stream that doesn't have any native timing ability, when the packet, as soon as the packet comes into our system, we timestamp it right as it's coming in, and there we put a 10 millisecond accuracy timestamp on it that is available later when you're decoding the instrumentation. So if you don't want to do anything, you've got a serial instrumentation, you will get that kind of accuracy in the system, essentially for free. Connectorization options, again, Deb talked about this. Each on the, you can either, when you're bringing an instrument on, you can bring in and have something that plugs in through a wet make connector onto the frame of the secondary node, and that's great because then we can add and take it away without having to plan on pulling the whole secondary node up. In some cases, though, that if we have a bunch of instrumentation that we know needs to be changed every year, that can be on a secondary node. It can all be hardwired in, and then we just plan on turning the node every year. And so, again, mostly we try and use the wet make connectors because it eases the maintenance operations for us. Here's just a quick eye chart of the pinouts. So at the end, on the secondary nodes, the end caps, they have dry bait connectors that then get converted to wet mates. But in either case, they've got 12 pins, and for the different ways that the system can be, or the interface can be connected here, this is what is available. And so in some cases, they have TOD, time of day, pulse per second, as well as like the 232 brings out the CTS or RTS. And so all that gets pre-configured. And this, I think these slides will be available with all this information after to the participants. So cable lengths, this is just the limitations of the different technologies out there that we try to be conservative so that we don't run into problems once we get on the seafloor and run into any issues with things marginally working. And so far, these rules of thumbs have worked well for us for everything we've put in. So the 232, try not to go more than 10 meters. 422, it depends on the data rates you're trying to get. We can easily get 500 meters at 200 kilobits, and we've gone as far as 1.2 kilometers for some of the short period seismometers. And then Ethernet, 70 meters is definitely the limit you want to put on that, and we've done that in a couple places without issues. Again, if you want to use, well, you'll need to use a wet make connector or dry make connector. If you want to use a wet make connector, then you'll need to work with ODI to make sure you get the right part so that it matches up with our system. And to that end, Dana has been working with ODI to make a tool to ease the process so that you're not starting from scratch every time you need a connector. And so you can work with ODI to figure out exactly the right combination of connectors, the lengths, and then this will help give you a price that you can put into your proposal. And I don't know if I know ODI was going to join this, but again, we can get this information out to you, and we'll work with you, and this will be part of the follow-up so that you're not dealing with them on your own. You know, we'll help you make sure that you're making the right choices and that there's no issues going forward, or any confusion with this. But this is a pretty nice tool just to quickly get the information and make sure we're all talking about the same thing going forward. All right, so this is a little bit of the process. Deb alluded to it, but you know, from our showing the different responsibilities for what the PI is responsible for what the PI and the MIOs work with together, and just how the flow goes. So you know, the top half, you know, so where we're at now is the initial scoping and proposal part. So you know, we'll have a meeting. We'll talk about what your needs are, what our availabilities are. There's a planning form that you can get or that you need to fill out to try and make sure there's no gotchas that we didn't think about in terms of power or distances or just all the different details, because there are a lot of details that have to get worked out. You know, we'll iterate through that, and then when we're happy with it, you're happy with it. Brian basically, you know, signs a form that says yes. You know, we think that technically this makes sense and we've covered all the bases, and then it goes into just the NSF approval process, and then once hopefully that gets approved, then we move to the actual development stage. And again, we'll want to be as integrated into your build process as possible, so again we don't run into any issues at the last minute. You know, but once that gets built, it's going to come to our facility, and we're going to do the standard tests we do on all of our instrumentation that's been put on, and I'll go through that in a little more detail. And then if something doesn't work, then it goes back to you guys to modify to pass those tests. And then finally, we'll you know, put together the final deployment operation plans and then deploy the instruments, and then it becomes part of the operations and maintenance at that point. Okay, so from our perspective, you know, the testing objectives that we're talking about here, you'll clearly have your own scientific testing and making sure the instrumentation does what you need to do. But from our standpoint, you know, we need to make sure that this is really ready to go onto a cabled system. You know, it needs to be a very complete, robust, functional. So we don't want to go through the whole process, put it down there, and have the thing fail. You know, that you know, for any reason at all. And we clearly don't want it to interfere with anything else in the system. So we want this to be a success, and the best way it can be a success is by testing early and fully testing it so that there's no issues once it gets put onto the system. And you know, the process that we have in place takes quite a bit of work, but it has resulted in a successful deployment of 30 different types of instruments over the last couple of years. So I think the lessons we've learned from that have paid off. Here's a list of the different types of instruments that are currently on the system and data flowing back that you can download and take a look at on oceanobservatories.org. Okay, I think this is yeah. So the process is, you know, every instrument that comes onto the system, you know, when it shows up at our site, we do a physical inspection and just make sure that, you know, what we're looking at matches the documentation, what we have. There's no obvious, you know, problems either when it was shipped or trying to put the thing together. And then we do a power on test. Okay, make sure that, yeah, we can talk to the thing, just simple the thing's up and working. A pressure test. So this one, either we do the pressure, we work with you to set up to do the pressure testing here at our site, or if you have done testing at your site and we've got documentation proving that it passed that test, then we don't have to do it here. But that's, you know, make sure the instrumentation works, but also a safety thing. You know, make sure that the ROV stays safe. We don't have any problems with that. Electrical characterization, this is where we'll use our equipment to look at inrush currents. We'll look for any potential ground faults in the system, make sure that the interface for the serial port or the Ethernet works correctly. We get a standard set test for that. We'll do an electrical isolation, and this is just to make sure that there's no connections between any of your power systems in the case. This is especially important when working on a cable observatory where you've got a lot of different instrumentation around. We don't want to have any spurious connections to seawater. This has been a trouble for some instruments, and we've had to iterate with the provider a couple times, or they'll be, they might be testing it differently, or they think they pass it, and it gets to our facility, we find out that there is an issue, and so that'll be one thing that we'll definitely need to work with you to make sure that there's no gotchas later. A burn-in, so let the system run, and depending upon the type of system, it might vary how much time, but we definitely want to let the system run for a while so it has some time on it before we try and deploy it. There'll be a full functionality test. Again, this is going through and making sure that we've tested all the different modes of the system. Sometimes you can run into issues where if there's some special function in the system that only get exercised a couple times, you might not see that there's an issue with it. And so full functionality, just to make sure we go through all the different functions of the system while it's connected up, and there's no unexpected results with that. Finally, there's integration with the secondary node. Up until this point, we might be working with either simulators or maybe a first article secondary node, but ultimately we'll definitely want to integrate it with the secondary node that it's going to be deployed on early in the process, and go through all the testing with that to make sure we've got all the cabling and wiring, everything's right with that. So some lessons learned. Obviously, material selection is important. Trying to put something connected to a cabled observatory for multiple years, need to make sure that you don't have lots of different types of materials on there. Ideally, it's titanium when possible, or if not, then very careful material selection's been done. Obviously, we're always testing for electrical isolation, throughout the process to make sure there's no unwanted interactions in the system. Design with deployment and recovery in mind. Clearly that'll be a topic of conversation. How will we get this down to the seafloor without breaking something, or it has the right weights, it's got the right handles needed so that the ROV can manipulate it as needed. Double check connector pinouts. We pretty religiously will go through and double check the power output on a connector before we plug it into anything. Just that it can get you if you don't do that. Need to understand electrical transients and noise sensitivity. So we have run into a problem where we'll have an instrument that looks like it doesn't take a lot of power. It'll be spec'd to use a very low amount of power. We'll plug it into the system, turn it on, and then we'll get an overcurrent. And and we'll look into it, and it has a whole bunch of caps on the front end, which don't matter if it's battery powered, but if it's off of a cable, it can be a problem. And we can account for that, but we need to know about it. We can also run into problems where, again, it's a low power instrument, but there's some mode that it can get into. Either it's self-calibrating or something else, and all of a sudden it'll use a whole bunch of power and cause an overcurrent condition. And so trying to make sure we exercise the instrument through all of its different modes as close to the installed environment as possible is really important, because we don't want to try to have to figure that out later after it's been installed. And again, thinking about cable lengths and voltage drops and community. So that's all the upfront stuff to really look at how much power the system uses and in all its different modes, and make sure we don't run into any unexpected situations. Another lesson learned, obviously, we're going on to a cabled observatory. Sometimes some of the instruments that we've had to use have been set up for the use case where, you know, someone has a GUI program for it, configures it, says save it, and then they go in and go off and run for a year in isolation, and then you bring back the system and get the data off of it. Well, that menu interface is great if you've got a person sitting at a computer, but not great if you're trying to interact with it with a computer program over the year. And so it's much easier if it's just a straight interface that a computer can deal with. Also, at all costs, as Dana put in here, you know, there should never be any commands that can get the thing into an unrecoverable state. And you know, again, we've gotten some instruments that they haven't really thought through that because their use model is you get it configured and then disconnect the cable and you come back a year later. Well, you know, some of them have had, you know, 2-character commands that can do, like, you know, a reset to factory defaults that changes everything, and if you get some noise on the communication signal, you know, there's no way to get it back once it's been installed. You know, and so those are just, you know, some things to watch out for, especially if you're developing a new interface or new software for it. It'd be good to maybe talk about that and see, you know, the easiest way to get it configured to work with the system best. Here's some of the testing facilities we have at UW and Ben Hall. We've got a chilled tank that we, you know, do some of our burn-in tests in. If it uses a lot of power and needs to be in a cold tank, we can run it there. We've got some power supplies and analyzers that we can use when we're running these instrumentations, especially for the burn-in test, to look for any anomalies. Installation resistance tester, and then a freezer that we can go through and do you know, longer-term cold tests on the system with. Also, we have a larger saltwater test. It's not chilled, but it's a larger test, so you can put, you know, the full-up integrated. So there's a secondary node we're putting in, you know, with the instrumentation that we can go through and do a full-up test on it to look for ground faults or interactions between instrumentation, and we can leave it in there over a weekend or longer if we need to. We also on site have a very large pressure test vessel where we do all of our pressure testing for the large secondary nodes and all the instrumentation. We also have a smaller one at APL if we need to, we can use. Just a sense of the different secondary, or some of the test equipment we have. We have some portable secondary node simulators. So these are rack mount equipment that essentially have all the same guts as the secondary node, all the same exact DC-to-DC converters and control electronics, but in a rack mount, and we can use those in the lab. And then we also bring those out onto the ship because one of the things we'll do is before it goes over the side, we'll do some, you know, final testing of everything to make sure, you know, nothing failed during transit, and it's all configured, ready to go onto the seafloor. We also have a smaller benchtop instrument port for a single instrument port, and those we can provide to people that are developing an instrument if they want to have an interface that they can test with at their site, or if we run into a problem while we're doing integration testing and they haven't been able to see it, we could send this back to them and they could, you know, get a relatively high fidelity test of the system with that. And then APL, you know, if you do need, you know, any extra engineering support, APL does have the, you know, we've done a lot of this type of work, and we can be available to help, you know, if any part of your design or proposal, if you need extra help with mechanical, electrical, or software, or extra testing, you know, we can be available for that as well. And any questions? We have there is that email is monitored by a number of, well, James, Dana, myself, and we're happy to support or answer any questions you have through the process. So appreciate the time and hope we can be working with you guys.
All right, it looks like we have some, thank you guys for that presentation, and it looks like we have some write-in questions. So first off, from Beth Levy, she says, you mentioned an international award. What country is that? And can you share the sensor type?
Not quite yet. We're still under discussion with them. It just came about, so we have some details to work out. but I will share with that it's multiple instruments. It's a pretty big effort, so we're excited about that. I'm assuming in February timeframe it'll, after we meet with them, we'll have some kind of announcement about it.
And next up, we have a question from Dave Dyer, and he asks, how much time is typically required for the test phase, i.e., how soon before deployment does the test phase start?
You know, ideally, I think, 3 months would be pushing it, I think, because I don't know if Dana, Dana didn't answer that question before, but I would think that that would be, at a minimum, I would think 3 months is when you would want to start that, and probably earlier. And, again, it depends on the type of instrument, how close is it is to something, or how complicated is it, and if it's, some interesting, unusual configuration, then we would want more time, but at a minimum 3 months, I think. And that would be part of something we would talk about, going forward, when we have the one-on-one discussions, what the timeline would look like for that.
And Dave, I can go ahead and unmute you for if you have any follow-ups. All right, go ahead. Looks like we're all good. Next up is Megan Tomlin asks, does OOI use a workflow tool to track where instruments are in their testing status, configuration, calibration cycle, etc.? How are these events tracked and documented?
Yeah, so we have a pretty extensive documentation process for all of this in terms of the test documentation is filled out as it goes through. I guess it's not a tool per se in that phase of it, and then all the calibration data is entered into oceanobservatories.org and used. So we get it gets entered into that, and that's what's used when the data is processed in the system. We also have a document repository for all the calibration data that's put on there. Yeah.
Yeah, and then in the operations center, once the instrument is installed, we have a logging system where anytime there's an issue with the instrument, that gets logged as well as the resolution. So all that is kept track of, and then of course asset management system in there too.
Another question that came in was whether or not these slides would be made available. And yes, we'll put a copy of the slides as well as a recording of this webinar on the OOI website, which is oceanobservatories.org. That's all I see for write-ins. If anyone else has another question, you can click one of the feedback icons or type anything into the Q&A or the chat windows.
So just to emphasize, we're really here to help you guys since it's a facility. So anytime you want to contact us, either whether before webinars or after for questions, you can come out and see us. Whatever we can do to help you ensure that all the information that you need for your proposal instrumentation is there.
And that's a good question, Deb. If someone wants to sign up for staff consultation, do you guys have specific dates that you're going to do those, or you're just looking for people to send you all a note?
No, they can. I think they can just send us a note. And there's information on the, if you haven't been there, on the oceanobservatories.org page under researchers, I think. There's more information about the proposal process, and it's, of course, it's always good to contact the relevant NSF program manager too to talk about it.
We got another question that came in. Let's see. It's from Lucia. It says, for every data product you have metadata, do you serve data products as a web service?
all the data, if I understand the question right, I mean, all the raw data are available through the data portal. Many of the data products are now available. Some of them are available through URDAP. And then, yes, the metadata for those, whatever the data products, are also available. The metadata also for sample information is available also through the data portal, or there's another access point. But does that answer the question?
I think so. And well, another thing to mention is that when we say available, we mean available for free. All the data is free to download on the website, and free to use in publications, free to use for your research.
And if you haven't been on the data portal yet, there's a login mechanism, but then for the instruments, there's quick views. So there's a plotting functionality. There's different, depending on the instruments, there's different plotting mechanisms to look at the data, where it'll give you a quick look at, you know, from day to year-long data sets. And then, you know, if you want a certain part of those data, you can put a request in through the data portal to get those data.
And if you have any trouble or have a question about any of the data or the data portal or anything with the OOI, you can also send a note to the OOI help desk. And you can get to that from our website. And the email for that is help@oceanobservatories.org. And that'll get you into our main help desk, and then we can forward your question on to the people who are best suited to answer it.
And although we've talked about, you know, getting infrastructure connected to the cable array, NSF is also, and has funded proposals to look at the data. So that's another opportunity there, as well as proposals to change, for science-driven questions, if you want to say, change sampling rates on the infrastructure, that's another way to write an NSF proposal to do that. Is that it?
That looks like it. Well, thanks everyone for coming to our webinar. Deb, I'll let you say goodbye.
Okay, yep. Please send us an email if we can help you in any way. Any questions you have, we'll do our best to answer them. So thanks a lot, guys.